Number 10. The average Mars astronaut will absorb more radiation on a single round trip than the current NASA career limit allows, and we have not yet decided what to do about that. Let us start with the one people think we have already figured out. Radiation. You have heard it mentioned. It gets a slide in every public presentation about Mars. What you rarely hear is the specific number sitting at the center of the problem. NASA's current career limit for low Earth orbit astronauts is set around 600 millisieverts for most crew members, adjusted by age and sex. A round trip to Mars, using current propulsion, would expose a crew to somewhere between 600 and 1200 millisieverts, depending on solar activity, shielding design, and mission duration. That number comes from measurements collected by the radiation assessment detector aboard the Curiosity rover during its cruise to Mars, published in the journal Science in 2013. That was a one-way trip with no human inside. The instrument still recorded 300 millisieverts just for the transit. Double it for the return. Add surface time. The math does not work under current rules. The strange part is not the radiation itself. It is the bureaucratic and biological knot it creates. Either you raise the acceptable cancer risk limit for astronauts, which involves ethics boards, legal exposure, and informed consent debates that have no clean resolution, or you build enough shielding to bring the dose down, which adds mass. And mass is the enemy of every Mars mission budget ever written. You cannot simply wrap the spacecraft in lead. Water walls have been proposed, polyethylene, habitat geometry that positions supply storage as a shield. Each solution adds weight, complexity, or both. Think of it like trying to drive across a desert where the road itself gives you sunburn. You can put up a sunroof, but you cannot enclose the whole highway. And the longer you drive, the worse it gets. This is the first item on the list because it seems solved in conversation, but is genuinely open in engineering. And it directly connects to the next problem, because the longer your transit takes, the more radiation you absorb. Which means transit time is not just a scheduling inconvenience. Number 9. Every serious Mars architecture assumes a fast transit, but we do not have an engine that reliably delivers one. Current chemical propulsion puts the one-way trip somewhere between 6 and 9 months depending on the launch window. The home and transfer orbit, the energy-efficient path, takes roughly 8 to 9 months. Nuclear thermal propulsion has been studied since the 1960s. Project Nerva proved the concept at engine test stands in Nevada. But no nuclear thermal rocket has ever flown in space, and the regulatory and political landscape for launching a fission reactor from Earth remains unsolved. NASA's current development program for nuclear thermal propulsion, running under the Space Technology Mission Directorate, is targeting a demonstrator in the early 2030s. That is still a demonstrator, not a crew-rated vehicle. What makes this strange is that the physics is not in dispute. Nuclear thermal engines can theoretically cut transit time significantly. The gap is not the science. It is the certification path, the launch licensing, the public perception risk, and the fact that nobody has built one that has ever operated above an atmosphere. We know what the engine should do. We cannot yet politically and operationally agree on how to get it off the ground. A useful analogy: imagine designing a car that theoretically halves your commute, but it runs on something you are not legally allowed to carry through any tunnel in the country. The engine works. The road is real. The legal framework does not exist yet. Shorter transit means less radiation exposure, but a shorter transit also means less time to prepare the surface habitat before the crew arrives, which introduces the next problem. Number 8. Pre-deploying a habitat to Mars before humans arrive sounds simple. The surface will probably destroy it before anyone lands. The current plan in most serious Mars architectures, including concepts studied by NASA's Human Research Program and the Artemis Forward Planning documents, is to send equipment ahead. Habitat modules, power systems, a propellant production unit. You land them. They sit on the surface for 2 years during the synodic wait period before a crewed mission can follow. And by the time humans arrive, the infrastructure is already running. The problem is those 2 years. Mars dust storms are not the cinematic wall of sand from popular fiction. The 2018 global dust storm that killed the Opportunity rover lasted roughly 8 months, and reduced solar irradiance at the surface by enough to starve a solar-powered system into shutdown. A habitat pre-deployed before humans arrive would need to survive at least one potential global storm, maintain thermal regulation through temperature swings that can exceed 100 degrees Celsius between day and night, and remain structurally sound under regolith that contains perchlorates, which are oxidizing chemicals that degrade many standard materials over time. The strange part is that we have very little real data on long-duration material degradation on the Martian surface. Most of what we know comes from rovers that were not designed to test structural materials. The InSight lander gave us seismic data, but its solar panels were slowly buried by dust over its operational lifetime, confirming the accumulation problem without solving it. It is like parking your house in a parking lot where every night someone throws salt on it. The temperature swings 100 degrees, and occasionally a storm buries it to the roofline. For 2 years, with no maintenance, the habitat surviving its wait period is not guaranteed. And the life support inside that habitat is a problem that does not get easier once humans move in. Number 7, every closed-loop life support system ever tested in space has broken down faster than its design spec predicted. The environmental control and life support system aboard the International Space Station is the most advanced human-rated system ever built, and it has required constant intervention from ground teams and resident crew across its operational life. A 2020 NASA assessment of ISS ECLSS performance documented recurring failures in the water recovery system and the carbon dioxide removal assembly, both of which are components that would be critical on a Mars mission. The difference on the ISS is that a resupply vehicle can reach it within 48 hours if something fails. On Mars, the next resupply opportunity is roughly 26 months away. What makes this strange is the nature of closed-loop failure. Systems degrade not in obvious ways, but in slow, coupled ways. A membrane fouls, a chemical bed saturates, a bacterial biofilm colonizes a waterline. None of these are dramatic. They are gradual and they interact. A CO2 removal system working at 90% efficiency means elevated CO2 levels which reduce crew cognitive performance, which means the engineers trying to fix the problem are already impaired. A feedback loop that gets worse the longer it runs. Think of it like a submarine, where the plumber, the electrician, and the air quality technician are all the same person. And all 3 systems are failing simultaneously, and the nearest help is 2 years away. The life support problem is tightly coupled to the next problem, because the same crew dealing with system failures is also the crew that needs to be medically functional to deal with anything else that goes wrong. Number 6, a Mars crew will need to perform surgery, manage psychiatric emergencies, and treat conditions that do not exist on Earth, with no real-time medical consultation possible. The communication delay between Earth and Mars ranges from about 3 minutes at closest approach to about 22 minutes at maximum orbital separation. That means a two-way exchange of information can take up to 44 minutes. If a crew member has an acute appendicitis, which occurs in about 1 in 1,000 people per year, the timeline for surgical intervention is hours, not days. A ground surgeon cannot guide a real-time procedure across a 44-minute round-trip delay. A 2021 paper in the journal NPJ Microgravity examined the medical autonomy requirements for long-duration exploration missions and identified over 100 clinical conditions that could be expected to arise during a 3-year Mars mission, many of which require procedural intervention beyond what any current astronaut medical training program covers. The proposed solutions include AI-assisted surgical guidance, robotic surgical systems, and extended medical training. None of these are crew-ready or fully validated for the Mars environment as of today. What makes this stranger is the psychological dimension. Prolonged isolation, confinement, high stakes, and the absence of familiar social anchors produce psychiatric conditions in analog mission studies. The HIC's missions in Hawaii, which simulated Mars isolation, documented interpersonal conflict, depression, and attentional degradation. On a real mission, those conditions would occur concurrently with technical system failures and medical incidents. It is like staffing an emergency room with a 5-person team that cannot call a specialist, has no resupply of medications after year 1, and is also sleeping in the same building they work in 7 days a week for 3 years. If you are watching because you actually want Mars to happen rather than just want to hear about it, this channel is where those 2 things are supposed to meet, and subscribing keeps that gap honest. Number 5. Getting a heavy crewed vehicle through the Martian atmosphere without killing everyone is still an open engineering problem, and the numbers are openly frightening. Mars has an atmosphere that is about 1% the density of Earth's at sea level. It is thick enough to heat an entry vehicle to extreme temperatures during descent, but not thick enough to meaningfully slow it down before impact. NASA's Mars 2020 mission, which delivered the Perseverance rover, used a supersonic retropropulsion system and a sky crane to land roughly 1 metric ton of payload. The largest crewed Mars lander concepts require landing somewhere between 20 and 40 metric tons. Nothing close to that mass has ever landed on Mars. The Mars Science Laboratory entry team called this the EDL problem, entry descent and landing, and referred to the gap between current demonstrated capability and crewed mission requirement as the 7 minutes of terror in public communication, though the engineering reality inside that phrase is more specifically the challenge of generating enough aerodynamic braking and propulsive force to slow a massive vehicle in a thin atmosphere without excessive fuel expenditure. Every kilogram of retropropulsion fuel you need to carry for landing is a kilogram you needed to launch from Earth or produce on Mars, which cascades through every other mission constraint. It is like trying to land a fully loaded 18-wheeler using only a parachute and a leaf blower in a 7-minute window with no retry. The landing problem connects directly to the departure problem, because once you land a crew on Mars, you need a way to get them back off it. Number 4. There is no confirmed plan for producing the fuel a Mars ascent vehicle needs on the surface of Mars, and without that fuel, no one comes home. Every credible Mars mission architecture that includes a human return assumes in situ resource utilization, or ICE-RU, to produce methane and liquid oxygen propellant from the Martian atmosphere and water ice. The Mars Oxygen In Situ Resource Utilization Experiment, called MOXIE, flew aboard Perseverance and successfully produced small amounts of oxygen from the Martian CO2 atmosphere across multiple operational runs between 2021 and 2023. That is a genuine milestone. Here is what MOXIE does not answer. It produced oxygen at a rate of roughly 10 grams per hour at peak performance. A Mars ascent vehicle using methane oxygen propellant needs on the order of 25 metric tons of propellant for a single ascent. The scaling jump from a toaster-sized MOXIE unit to a propellant production plant capable of filling a rocket over 2 years is not incremental. It requires a power source, almost certainly nuclear, a water extraction system that has never operated on Mars, cryogenic storage that has never operated on Mars, and a methane synthesis reactor that has never operated on Mars, all running continuously for roughly 26 months before a crew arrives. In a dust and temperature environment we cannot fully simulate on Earth. The strange part is the dependency chain. Everything downstream of the mission, the ascent, the transit home, the cruise, survival guarantee, depends on a factory that has never been built, in an environment we have only partially characterized, running autonomously for over 2 years. It is like planning a road trip, where you have not built the gas station at the destination yet, the construction crew has never been there, and if it is not finished when you arrive, you simply do not go home. Number 3, Martian regolith is not just dirt. It contains a class of chemicals that would damage human lungs on every EVA, and we do not have a reliable way to stop them from getting inside. Perchlorates are oxidizing salts found throughout the Martian surface at concentrations between 0.5 and 1% by weight in soil samples from multiple landing sites. They are toxic to human thyroid function and are suspected lung irritants. Mars dust particles are also extremely fine, with some fractions in the nanometer range, and the low-gravity environment keeps them suspended longer than comparable particles on Earth. Every EVA a crew member conducts brings dust back inside on suit surfaces, tools, and equipment. Apollo crews dealt with this on the Moon. The lunar surface left abrasive material inside habitats and coughed up in post-EVA medical checks. Mars is worse because the chemistry is active, not inert. Number 2, Mars and Earth only align for a launch window every 26 months. Miss it with a broken system, and you wait over 2 years in a place that was trying to kill you when everything was working. The synodic period of Mars relative to Earth means the planets are only in optimal launch alignment approximately every 26 months. This is not a political or engineering constraint. It is orbital mechanics. Every Mars mission architecture is built around this window as a hard deadline. If a crew needs to abort and return to Earth before the window opens, they cannot. If the ascent vehicle fails to produce enough propellant before the crew arrives, they wait on the surface while the clock counts down. If a crew member becomes critically ill at month 18 of a 36-month surface stay, the earliest evacuation scenario is still tied to orbital geometry. The Apollo 13 mission survived because the Moon is 3 days away. A Mars emergency is a minimum of 6 months from Earth, even with the fastest imaginable future propulsion. Every failure mode on Mars is compounded by the impossibility of coming home early. Number 1, we do not know what happens to the human body after 3 years at Mars gravity, and we cannot find out until we go. Mars gravity is 38% of Earth's. The longest continuous human spaceflight record, set by Oleg Kononenko aboard the ISS, accumulated over a year in microgravity, not partial gravity. The effects of prolonged partial gravity on bone density, cardiovascular function, muscle mass, vestibular adaptation, and immune response are genuinely unknown. The ISS data is microgravity data. Centrifuge studies on Earth give us partial information. No rotating habitat generating artificial gravity has ever flown. There is no validated countermeasure protocol for 38% gravity over 3 years, because no human has ever experienced 38% gravity for more than minutes during a suborbital arc. This is the final problem, not because it is the most dramatic, but because it is the most honest. Every other problem on this list has a proposed solution, a research program, a test article, or at least a defined failure mode. This one has a blank space where the data should be. We are planning a mission to send humans to a place where we do not know what will happen to their bodies, because the only way to find out is to send humans there. The dream of Mars is real. The checklist of what we do not know is longer.